Now we're ready to look at finding optimal mixed strategies and values of a game for games that are larger than 2 by 2. Remember back when we studied game theory back in Unit 2, we looked at games 2 by 2 for optimal mixed strategies. So now we're going to look at games that are bigger. I do have a refresher that you're asked to do kind of before the lecture, is finding the row player's maxi-min and the column player's mini-max. I have done that here. One thing I do want to point out is this game is not strictly determined. Okay, remember, games that are strictly determined have optimal strategies that are pure. So when we're asked to solve a game, which means find optimal strategies and the value of the game, we should always check to see if the game is strictly determined first. That still holds true just like it did back in Unit 2. Because if the game is strictly determined, optimal strategies are pure, and we do not need to go through any of the mixed strategy processes. Okay? So, how do we solve a game that's bigger than 2 by 2? We'll start by solving this game in the before the lecture that is not strictly determined. Our first step is to add a fixed number k to each entry to the payoff, so that the entries in the matrix become non-negative and no column is all zeros. I typically look for the smallest number and then add its opposite. So in this case, the smallest number is -2, so we'll add the opposite of -2, which is 2. So you can use 2 or any number bigger than 2, and it doesn't matter. You just get a different looking game and a different looking matrix when we go through the process. I'm going to use k equals 2 because the smallest number in our game is -2, and I can add everything, or add 2 to everything, and make sure every entry is greater than or equal to 0 and no column is all zeros. So when I add 2 to this game, it gives us the new matrix, or the new game, 5, 1, 2 across the top, 0, 3, 1 across the bottom. So we write 1s to the right of and below the payoff matrix. So to the right and below. And then we kind of write the associated standard maximization problem in the following way. The bottom row is going to be our objective function. So we're going to maximize P equals x plus y plus z, subject to 5x plus y plus 2z less than or equal to 1, no x's, 3y's plus 1z less than or equal to 1, and of course our variables are not negative. So we've created a standard maximization problem from this game. And the next step is to solve this standard maximization problem. Once we solve this problem, we'll be able to get solutions for the optimal strategy of the column player, optimal mixed strategy of the row player, and value of the game. Please note that the column player has 3 moves, and we have 3 main variables. The row player has 2 moves, and we have 2 constraints, which means we'll have 2 slack variables. Okay. That is a big hint as to what's going on. So, how do we get our solutions or our strategies from the final tableau? So here we have the final tableau. We can list our active variables if we need to. Z is active in row 1. Y is active in row 2. So our solution, x equals 0, y equals 1/5, z equals 2/5. So how do we get the optimal strategy for the column player? We take our solution to the standard max problem, the x, y, z variables, and express them as a column matrix. And then we take that column matrix and multiply it by the reciprocal of P. So the optimal strategy, optimal mixed strategy for the column player is the reciprocal of P times the solutions. So in this case, P was equal to 3/5. So 1 over P is 5/3. We've already said X is 0, Y is 1/5, Z is 2/5. We'll do our multiplication. 0, 1/3, 2/3. And note, the entries in the strategy matrix do add to 1, just like they should. Now, the strategy for the row player is determined using dual solutions. So we're going to look at the bottom of the slack variable column. Okay, so again, we will multiply by 1 over P, or the reciprocal of P. We have two slack variables. We looked at the solutions to the dual problem, so the bottom of the slack variable columns, 2/5, 1/5. So the reciprocal of P, S1, 2/5, S2, 1/5. We'll do that multiplication. Get 2/3, 1/3. And again, do note those do add to 1. So there is the row player's optimal mix strategy. To get the value of the game, we simply use the formula E equals 1 over P minus K. And this formula will be provided on the test. So we do need to remember what the K value was. Remember, K is what we added to make all the entries non-negative. 1 over P is the reciprocal of P, so 5/3. We added 2 to every entry, so 5/3 minus 2, which is negative 1/3. That means the game favors the column player, correct. Okay, that's really all there is to it. Add number to the matrix to make sure you have no negative entries. Put ones to the right and ones to the bottom, and create a standard maximization problem. Solve that max. Solutions to the maximization problem represent strategies for the column player. Solutions to the dual problem represent strategies for the row player, and we'll use this formula to get the value of the game. So let's take a look at another example. Top of page 3. So here we have a 3x4 game. The row player has 3 moves, the column player has 4. We should check to see if it is strictly determined. A quick check. So circle the worst in each row for the row player. Box the worst in each column for the column player. And we see the game is not strictly determined. Optimal strategies are indeed mixed. So we'll proceed. So the value that we want to add to each entry, the smallest number we can get away with is 3. You can use 3 or anything bigger. I'm going to stick with 3. That gives us the new matrix 5, 2, 1, 0 across the top, 4, 5, 3, 4 for the second row, 3, 5, 6, 6 for the third row. Then we'll put our ones to the right and our ones to the bottom, and we can now write our standard maximization problem. We're going to need 4 variables, so maximize P equals X plus Y plus Z plus W, subject to 5X plus 2Y plus Z less than or equal to 1. 4x plus 5y plus 3z plus 4w less than equal to 1. 3x plus 5y plus 6z plus 6w less than equal to 1. And of course, x, y, z, and w are all greater than equal to 0. So we've created our maximization problem. We're now ready to create our initial tableau and go through and solve. Okay, so there's our initial tableau. We do have a tie for the most negative number in the bottom, so I've always said go to the far left. That's our pivot column. We'll do our ratios: 1/5, 1/4, 1/3. 1/5 is the smallest, so we'll pivot in row 1, column 1, giving us this matrix. We still have negatives in the bottom, so we're not done. The most negative, -1, so that means W will be the pivot column. We can't pivot on a 0, so there's no ratio to do there. 1/5 over 4 is 1/5 times 1/4, 1/20th. 2/5 divided by 6 is 2/5 times 1/6, which is 2/30ths, or 1 over 15. The smaller of these two is 1 over 20. So we pivot here. Performing the pivot will yield this third tableau. Again, we still have a negative number in the bottom. So Z is our pivot column. 1/5 over 1/5 is 1. 1/20th over 11/20th is 1 over 11. 1/10 over 21/10 is 1 over 21. The smallest of these is right here in row 3. So we'll pivot in row 3, column 3, giving us this final tableau. We know we're at the final tableau. There's no negatives in the bottom. Remember, this did start off as a standard max. Alright, so the column player, the reciprocal of P, times the solutions to the maximization problem. Remember, the column player does have 4 moves. 1, 2, 3, 4 columns. So we should have 4 entries. X, Y, Z, W. X is 4 over 21. Y is inactive, so Y is 0. Z is active and equal to 1 over 21. W is active and equal to 1 over 42. Now remember the reciprocal of P, so that's 42 over 11 times these: 4 over 21, 0, 1 over 21, and 1 over 42. Multiplying that out, we get 8 over 11, 0, 2 over 11, and 1 over 11. For the row player, it's the reciprocal of P, 42 over 11, times the dual solutions, S1, S2, S3. And I'll remind you, dual solutions. So S1 is 1 over 14. S2 is 1 over 14. S3 is 5 over 42. Simplifying, 3 over 11, 3 over 11, and 5 over 11. So there's the row player's optimal mixed strategy. And again, note these do add to 1. The expected value, 1 over P minus K. So the reciprocal of P, 42 over 11 minus K. We said K was 3. So 3 is 33 over 11. 42 minus 33, 9/11. And so this game would favor the row player. Now, we see the row player is going to play row 3 most of the time. The column player is going to play column 1 most of the time. And when we look back at the game, it does make sense that the column player is going to play column 1 a lot, knowing the row players play in row 3 a lot. When we look at row 3, the best outcome for the column player is indeed in column 1. Okay. All right. We're now ready for our last page. If I can get the page turned. Okay. So, one more example, and this will be similar to what's on your test. So we have a 3x3 game. Quickly see that it is not strictly determined, but we'll do the circling. And then we'll do the boxing for the column player. And we see the game is not strictly determined. Optimal strategies are mixed. Okay, so value of K. Smallest number in the game was a -2, so we'll let that be 2. Adding 2 to each entry in the game, the top row becomes 1, 3, 4. The second row becomes 4, 1, 0. And the third row becomes 3, 4, 2. We write our ones to the right and below. And we can create our standard max problem. Maximize P equals X plus Y plus Z, subject to X plus 3Y plus 4Z less than or equal to 1, 4X plus Y plus no Z less than or equal to 1, 3X plus 4Y plus 2Z less than or equal to 1. And then of course X, Y, and Z are all greater than or equal to 0. We can then create an initial tableau and go through and solve it. I have done that for us and provided us with the final tableau. So we're supposed to use this tableau to find the optimal mixed strategy for both the row and the column player. So let's start with the column player. 1 over P times the solutions to the maximization problem. So X, Y, Z solutions. 1 over P is 5/2. Solutions to the maximization problem. X is 1/5. Y is inactive, so it's equal to 0. Z is active in the third row, 1/5. Do our multiplying and we get the optimal mixed strategy for the column player is 1/2, 0, 1/2. We look back at the game, they're playing the middle column never, which makes a little bit of sense. There's not much difference in the first column and the second column, just numbers are arranged differently. So probably has something to do with the row player strategy. So let's take a look at the row player's optimal strategy. R equals 1 over P. Then the solutions to the dual problem, S1, S2, S3. And again, I will remind you, dual solutions. Even though the dual problem is technically a minimization problem now. Alright. 5 over 2 S1 is 1/10. S2 is 0. S3 is 3/10. Doing our multiplication, 1/4, 0, 3/4. And we're ready to find the expected value of the game. Before we do that, we'll revisit the row players play in row 1, 1/4, row 3, 3/4. So clearly if row 3 is played a lot, like it is, the column player is going to play column 3 quite a bit. On the off chance that row 1 gets played, the column player does want to play column 1 in that case, so we see the 1/2. Of course, not much difference in breaking even and losing 1, but there is a difference. So that's kind of what's going on there. Our expected value of the game when these strategies are used, 1/p minus k. I'll slide that up so you can see it. 1/p, 5/2 minus k. Remember, we did say k was 2. So minus 2, which is 4/2. So we get a value of 1/2, which means this game does favor the row player. That's it for mixed strategies of games bigger than 2x2. We'll have more problems with this in class or in our Zoom session on Wednesday, March 25th, and Friday, March 26th. Let me know if you have questions.